And I do appreciate the fact that you chose a day when the weather matches my expectations of Ann Arbor. What I want to do is to talk a little bit about some aspects of the way in which we view the world that we normally don't think we can very effectively and formally model. And today, formally is sort of if we can build a computational model of it, rather than if we can build a partial differential equation, say. So what is meant by social? Of course, I could start off by asking what is meant by design, but we don't have much time. I could ask what is meant by computation and see whether you understand this amazing revolution that has been that we're in the middle of, but we're not going to do that either. We're going to talk about social. And by social, I don't mean how you shake hands and how you talk to people. What I mean is the idea from Weber that social interactions are always about information passing. And let me see if I can give you a simple example, which turns out not to be that easy at all. So let me do this. Social interactions are about information. And let's say this is the formal interaction. We've got A and A1 and A2. We've chosen A because we're going to end up with agents, right? And A1 says, can you do task T1? If yes, can you pass the resulting task T2 onto A3? And the response from A2 is, yes, I can. But there's all this other stuff that turns out indirectly is also occurring. And I want to suggest that this direct and indirect interactions that occur between people play a role in design. And normally, we just don't deal with this. We think of design of technical systems and engineering systems as being associated with ideas about the product. What are the requirements for it? What are the componentry? How do we break it up? Do we isolate it by domain systems? Do we isolate it some other way? Do we do this? Do we build models of it? Do we build visual models of it, manufacturing models of it? As if we live in a world where there's no humans. And most of you probably realize that that's not true. In fact, our world is occupied by humans. So that's what I want to talk about. If you want to talk about humans, though, you need to talk about humans. How do we talk about humans in a way that allows us to abstract some mental activity? That's a field called cognitive science. But cognitive science, it is a big field and full of interesting issues, and I want to talk about a particular view inside cognitive science and my view of that. And this is called situated cognition. If you go to the literature, situated cognition conflates with embodied cognition. It's the notion that cognition, which is the mental, it's what happens in your mind, not in your brain, can't occur outside something. So humans have it because it's in us, and robots have it because it's in them. And that's where you see all this. I, however, I have no problem with that, but I want to introduce you, and I'm told you're actually all very smart, so I'm going to give you in 5 or 6 slides what takes a 13-week semester to get through. So if you don't get all of it in those slides, that's the reason why. But you'll get some idea of it, right? Just some inkling of it. So let's start off with some like aphorisms, which normally you don't associate with computation. Where you are when matters. You think, come on, how can that, I look at the equations of motion, and they've got nothing about me in it. And that's true. Until Einstein comes along, of course, and it turns out you are there somewhere. Because it depends what speed you're traveling at. But where you are when is a quite profound idea. And let me show you this little toy example. Now, here's an image. And if you come from the art world, you recognize this. This is Gero. But anyway, it's an image. And let's say you saw this a couple of days ago. And let's say yesterday you saw this image, and maybe you say, oh, I think I've seen that. But unless you're right there when this appears, which is these two images juxtaposed just like this, you don't see this emergent shape. And depending on what sort of person you are, it's either a champagne glass or it's a vase. But that thing is a function of the contemporaneousness of those images. Where you are when matters. Not all the time, but sometimes. What you're looking for affects what you see. Now here's a little experiment that goes like this. You're the participants. No IRB required because we're not measuring anything, right? About you. I'm going to ask you to close your eyes. Not yet, I'll tell you. Close your eyes. I'm going to put something up on the screen. And then I want you to read aloud in your head what's on the screen, okay? So everybody, please close your eyes. Yes? Okay, open your eyes. Read aloud in your head what's on the screen. Is there anybody who can't read this? And you get better at it, you notice. Towards the end, it gets quite easy. But wait a minute. What's up there is not English at all. It's sort of randomly distributed letters. But you can, it's your type. It's your and my typing looks like this, I know. But how is this possible that you can read this garbage? It's because I set up an expectation. So maybe what's in our heads isn't a copy of what's outside at all. At all. And there's some fundamental biological reasons to support this, apart from this nice cognitive evidence. If you know anything about your own physiology, you may know that for some unknown reason, the optic nerve passes through the retina. If you don't know, I'm telling you. The effect of this is that right in the middle of your eye is a hole in the sense that there's no sensors there, no rods or cones. When you look around, do you see a hole in your vision? You should, because you're not sensing anything in the center of your vision. Why don't you? It's because you make it up. What's in your head and what you sense are just not as correlated as you might imagine. Now, we're accustomed to building models of the world that we're trying to design. So we have these CAD modeling systems, we have mathematical modeling systems, and we somehow or other think they're veridical. That is, they contain something about the world in them that tells us about the world. So here's another little experiment. I presume everyone can see these triangles that have vertical bases and they point from left to right. Okay. I'm going to show you another image and ask you, this is not the image, this is the in between. So here's the other image, and you can see that triangles here have their bases pointing this way, and then they point up from bottom left to top right. Everyone see that? The question is, how many people took the original triangles and then rotated them to get these triangles? Anyone do that? Typically, 1 in 100, 1 point something in 100 do that, which tells us something about them, but I'm not going to tell you what it is because there's nobody here like that. But if you didn't do that, this is a different image, just a different representation. Same image, different representation. So what you see is not what you get at all. And what's in your head doesn't come out always. Two different things can be the same. So humans are a little richer, actually a lot richer, dramatically richer, than the sort of modeling we're accustomed to doing. So that's some entree into the notion that when humans deal with the world, there isn't this one-to-one homomorphism between what's in your head and what's outside. Whether what's outside are words that you say, words that you type, images that you draw, things that you see, none of those is there a homomorphism in the cognitive mind. So where does this leave us? Well, first we have to understand even more. This next thing is that interactions between people play a fundamental role in two things at least. The first is the way in which you think the world is structured, because it's to do with what other people think. There's a beautiful line by John Donne, "No man is an island." And I'm not quite sure what he meant by it, because he's a profound, in this case, poet, but the notion being that we are a consequence of our interactions. And there's two fundamental kinds of interactions, which we saw in that second slide. Direct interactions, and we're accustomed to those between people, but now, of course, between people and artifacts. And increasingly with the Internet of Things, there's between artifacts. And then there's all these indirect interactions, which is, when we see the, I've got to be careful here because I'm in Michigan. I was going to say the President of the United States shaking hands with Putin, say. We're not even there, but that tells us something, right? So observing interactions and so on. This notion of interaction is another one of these profound ideas that you think, well, wait a minute, I'm sort of doing design, I'm doing engineering, that's got nothing to do with me, except that if I'm working in a team, it has everything to do with you. And how we go? Oh, we started late, right? So we're okay. My flight's at 2:40. I have to leave here at 2:45, so got plenty of time. Let me give you a little example. I presume even though you're graduate students, you still they give you time to go to the movies, right? Or watch movies. And some places don't, because you're not working hard enough. So here's an example. You go to the movies with some friends, or the cinema, and while you're sitting there, you think, this is the worst movie I have ever seen. Really, I mean, truly, truly bad. I don't know if you know the movie The Room, but it's that kind of movie. I've been to movies like that because I had a lot of children, and you go to movies as an adult you wouldn't normally go to, but they love them. But anyway, you come out, and before you can say anything, your friends are saying, what an amazing movie. Did you see the symbolism in that? That dead, flat sea, that wasn't poor computer graphics, that was death. And you see the Hitchcockian angle about how, shot down from above the ceiling. Okay, you listen to all this discussion. Now you go back to your home, or dorm, or wherever you live. What are you going to tell the people there? Are you going to say, I went to this really bad movie? Or are you going to say, I went to this amazing movie full of symbolism? You didn't experience that. It's a consequence of your interactions. And as a consequence, we can start to think of what happens cognitively. Now, this idea of memory is an interesting one, and it's interesting in multiple ways. The first is, in the US, it took like 20 or 30 years to reach here because it wasn't invented here. And, the US is every country is like this. If it's not invented here, it's not as good. I had a Russian postdoc who was absolutely surprised to discover that refrigerators were invented in the US because he thought they were invented in the Soviet Union, and so on. But this work is by Frederick Bartlett, a British psychologist. He said that, today, he didn't say this, today we somehow or other are seduced by the way that computers work, that therefore maybe humans are like that. Memory being a thing in a place, right? Which is the way it is in a computer, and you can pull it up and do things to it. The evidence for that in humans is pretty low. Okay, firstly, memory is distributed, but more importantly, there's something else going on. Really something else going on. And that memory is a process. And let me see if I can describe it to you. Let's say you actually have sensate experiences. That is, things that you sense in the world. But we've already found that your sensate experiences themselves are pretty dubious, right? But it doesn't matter, you had them. Now, you've got to be careful about sensate experience. There's a famous discussion between Ludwig Wittgenstein and Bertrand Russell. Bertrand Russell was a great philosopher in the early part of the 20th century and wrote Principia Mathematica with Alfred Whitehead. He was a really serious person. And Wittgenstein was a truly influential philosopher starting off in the 30s, and he was Russell's doctoral student. And therefore, what they had to say to each other is interesting. So Wittgenstein says, you can say there's a desk here, but you can't say there's no rhinoceros here. Because you can sense the desk, but you can't sense the absence of anything. So you've got to be careful about what is your experience. Because when I say there was no rhinoceros there, that wasn't something I experienced. I made that up. So right there's a nice simple example. If someone said, was there a rhinoceros in the room when he was talking? And you were going to say, no. But that doesn't come from memory. You constructed it. So let's see if we can just follow this a little bit more. So I'm going to use this word situation and leave it open, just meaning the world you're in. And you ask a question. And maybe the question can't be answered by just pulling up your experience, which is what a computer memory would look like. Maybe it needs a number of these, and it gives you an answer that isn't one of these experiences, so it's a new one. Was there a rhinoceros there? No. Well, now that's in your memory, but you made it up. So this is a constructed memory. And this is knowledge that you have about how to put the world together. And because of the existence of this memory, you've sort of changed a little bit. Now you can ask another question, and maybe it still uses these things you sensed, your sensate experience, and now you construct another memory. But after a while, it needs, the third one starts to use memories you've constructed. And then they start, and you don't know anything about this, you start to use all these. So these constructed memories don't look any different to you to the memories of the things that actually happened to you. But then more and more happens, and I don't have time to go through it, but it is important, that these, as there's more and more of these, the significance of these gets less and less. Not only that, this experience, this one here, is connected to this memory and connected to this memory, and also because it's connected to this memory, it's connected to another memory. So it turns out this experience doesn't sit by itself. It's connected to things that happened after that. And the meaning of this changes. Now, what could that even mean to us? What it says is the past for humans is not fixed. Now, there's great novelists and writers who can put themselves, in the mind of a 16-year-old when they're 40. But we can't. Most of us can't. All you can be is a 40-year-old pretending to be a 16-year-old. But you can't be a 16-year-old anymore. Now, this is a really important idea in designing, because designing is a temporal process. And things that happened before, obviously, wherever they are, get used again and get changed by that. The meaning. So there's a beautiful line from John Dewey which says, talking about experiences, and he didn't distinguish between these two, although he's one of the people who showed that there's actually a physiological basis to this called the reflective arc. But he has this beautiful line. He says, subsequent experiences structure and hence give meaning to what was experienced before. Okay, so what can we now say about this? That memory is a reasoning process. It's also just a selection process as well. But it's not like a computer. If you don't know how to get here, I mean, I was in the optimization lab, and I've got to say, to get here I stopped counting at 14 turns, right? It must be more than 14. Now, to get here wasn't that straightforward, and I wasn't looking because I had guides. But we all know this. The first time you go to a place, it's really hard. And so always coming back from there is much easier. And then after a while you learn how to do it, because there's other things going on, like reinforcing what facts look like for you. So not everything is reasoning, but it's always a process. For humans, you don't need to have an index. Of course, in computational systems, we have non-index systems as well, associative memory. And when you do have an index, the index is changed by what you've been doing with it. So, that memory down here that was used in this one and then later used in that one and that one now has different kinds of indices connected to it. The content can be changed by its use. So you get memories that get conflated and pulled apart. And then finally, something which we can now model using constructive neural networks, the structure of the memory itself changes by its use. So this is a really rich world. And, well, that's sort of the same thing. And here's John Dewey. I thought I'd take that out. So we've got interactions, we've got constructive memory, and then we've got this third idea called situatedness. What is situatedness? Something like your worldview, what you think the world is actually about. It's the sort of thing that gives you, your value systems, your expectations about what's going to happen. And let me give you a nice little example. And if you've seen this before, don't say, oh, I know the answer. It's not that kind of test. Right? It's a test from psychology, and psychologists don't have that much imagination. It's called the 9-dot test. And the test is this: draw 4 straight lines without lifting your drawing implement from the medium so that every dot is passed through at least once. And this is a typical sort of thing. Here's 1 line, 2, 3, 4. Whoops, 1 left. And if I were to give you this task, not set up quite, just set up the task, but not show you, 60 to 70% of you will work out that you can exhaustively go through this and show that you can't do it. There is no way of getting 4 lines to pass through that. But of course there is, otherwise I wouldn't put it up. And it looks like this. And you know what people say? You never told us you could go outside them. The dots, I never said anything about where you could go. That's a world that you've constructed, so that's the situation you're in that makes, if you think that's the way the world works, it works like that. We do that all the time. And in fact, that's, to me, a fundamental idea about human cognition. Okay, here's a little example. I show you this photograph. I tell you devastation produced by Hurricane Katrina. Now you have the meaning. If I show you the same photograph and I say an example of unsafe demolition practices, sure. It's actually neither of those. It comes from a cyclone in Australia, in Darwin. Don't go to Darwin during a cyclone. So situations give you values. Now this is beautiful. 6, no, 9. It depends what world, here it's a physical worldview, right? But then humans have this special characteristic, I don't know about anything else, but we know only about humans. Just because you're right doesn't mean I'm wrong. See, that's a profound idea. Humans actually, the same person can think both of those things contiguously. At the same time, I don't know, but contiguously you can test. Okay, so what are the basic ideas if we're going to build social systems? Knowledge comes from interaction. Actually, I haven't talked about stigmergy. Anyone know what stigmergy is? Hang around then. Memory is from construction, not just recall, and situations give meanings and expectations. Expectations are profound. All of these are profound ideas. I can use those. Normally I spend a little more time getting here to develop a set of principles. The principle of effect, which we normally don't consider, and we don't want to consider. If I use a spreadsheet, and then I use it for another set of data, nothing has changed in the spreadsheet. And actually, we don't want it to change. But there's another world where when I do something, we do want things to change. So that what you do matters. And you can't help it matter once you're involved socially. You know, if somebody, you have a partner, and they say, I'm going to leave you, you can't take that back. I mean, they don't have to leave and so on, but something's happened. That's going to be there. What you do matters. The principle of ordered temporality. When you do what you do matters, right? And these are so obvious, right? You know, if you leave home before this is a silly example, before you put your clothes on, that's sort of unusual, but you just change the order and everything's fine. Right? The lemma of experience. lemma is a consequence of a theorem. What you did before affects what you do now. The principle of locality, where you are when you do what you do matters. You notice these are nested principles. The principle of interaction, who and what you interact with matters. And then finally, the principle of ontology, what you think the world is about affects what it is about for you. You know, if I pointed to someone and said, get undressed, I would hope everyone would think that's pretty out there, and more than that. But the same two people in a different situation, and I said, get undressed, would be very reasonable. I'm your doctor, you're my patient. You say, I've got this big rash all over me, and I say, get undressed. You wouldn't think, my God, what's going on here? So it's not the act, it's what you think the world is about. Okay, can we now start to build systems that embody these ideas? And of course the answer is yes, otherwise I'd stop here. And we use, you don't have to, but a good implementation concept are agents. Agents are, I mean, computer science and AI loves to make big claims. They're autonomous computer systems. Well, they're autonomous in the sense that we designed them in such a way that they will continue to run. They're not autonomous in the same way humans are autonomous. And that's because we don't know really enough about humans. But basically, the sort of things we want in them are the things we've talked about. We want them to be affected by interactions. We want them to be social, meaning there's stuff passing back and forth. We want them to be cognitive, so that these things we talked about are involved. And therefore, they become adaptive. Means they change. Doesn't mean that every interaction produces a change, but every interaction should have the potential to produce a change. And that's not the kind of world we're accustomed to building. And then they should be stigmergic, or offer the... Stigmergy is an interesting idea. It's coordination without collaboration. It's what you see in ant colonies, right? And we'll see an example of that. All right, so here's a little example. And it's adaptation through stigmergic social behavior. And it's going to demonstrate a couple of the things we've seen. And what I want to do is to study people going through doors. Of course, what I could do is I could build a Gaussian distribution of arrivals. So it's a source-sink model, service model. I could build a Poisson distribution of service, which is the door, and solve these equations if I could think carefully enough, and give you some answers of some kind. But I can do it in a very different way. What I'm going to do is build an agent-based model that uses a social force model. It comes from Reynolds' work, the idea behind this, although not the rest of it. And we're going to make it situated. The agent has 4 rules in it. That's it. The first one is it tries to go from A to B as efficiently as possible. What does that mean? They're not going to hang around. You could build one which people hang around if they see friends, right? I don't know if you come across the notion of personal space. Does that mean anything? Yes? No? I'm thinking of yes. Someone's nodded their head. That's good. You know, for those who don't know, humans have this really interesting idea, which is very cultural and very situated, about how close they let other people come to them physically, right? So if I'm looking in a shop window, there's still shop windows around, and someone comes up behind me and pushes against me, in most states, that's actually assault. Unless it's my girlfriend, or my wife. Actually, if it was my girlfriend, that would work too. So that's assault. But if I'm in an elevator and I push, 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 and now I'm pushing against the person behind me, that's not assault. But people like to keep distance between them. So this is try and maintain a comfortable distance. We separate our people from things because things are unyielding, right? So objects. And I don't know if you've ever seen those little movies of ducklings following their parents around. Humans do this too, by the way. Not with ducklings, but with each other. And you've probably seen this. You know, you're walking down the street and somebody tilts their head up. And the next person tilts, and then everyone looks up. Because the first person had a crick in their neck. They were doing this to get rid of it. So, you know, humans are followers. So, 4 rules. We build an environment and we just let the black circles start on the left and they just want to go to the right, and the white circles want to go from the right to the left. We didn't program anything beyond that except where they are based on these 4 rules. You know, and they're struggling through this door. It's hard work, by the way. But we collect statistical information and we can build up the distribution of behavior of this population of people trying to get through the door and the door. And then we can do the same. Everything's the same, except now we have 2 doors. We just started it again, but now we have 2 doors, and away they go. Again, there's no programming of locations or anything, so this is a phenomenological result. We are generating phenomena, not observing phenomena and modeling it, right? So we're actually generating what otherwise you might go out and capture and try and build a model of. And then we allow adaptation. What can be adapted here? There's only 4 rules. So the only thing you can do is fire a rule in front of another rule. That's what adaptation will produce. So all it does is, each one of these, when it goes through the door, looks back and says, what was the last rule I used? And I'm going to give that a higher, that's what it means. I mean, it's just a standard machine learning approach, but what it does is it basically says, I'm going to elevate the last rule I used, give it more importance. The next movie is actually, I think, quite short, so watch it. It's so short you didn't even see it. So, it really is short. You notice the black ones went more and more from down the bottom, and the white ones more and more on the top. No collaboration here. They don't know anything about the others, but they produce what is called acculturation. That is, a set of values that drive people without any explanation or any model. And you see this all over human behavior, like pedestrians passing each other on the street. They use visual cues, and you can find all those really easily when you study it. But what's interesting is when they fail, you don't know what to do. And people do this dance because you don't have a model. It's not like pass on the left. There is no model for it. So stigmergy, that is coordination without collaboration. Okay, well, turns out you can do it this way. I want to now move fairly quickly to show you some other examples of implementations of varying scales and depth. So this is the influence of social ties on teams in terms of the diversity of new ideas they generate. What is meant by a social tie? It's a technical term It refers to how close your values are to the other members. It comes from studying tribality. In teams, what you see is this. This is not what this is showing. What you see in teams is as teams work together, so their value systems start to converge. That is, they change over time. Here, what we're going to do is we're going to plot, just in an absolute sense, the strength of social ties against a measure of the diversity of ideas. We use Gini coefficient. Is that? The Gini coefficient is a term from economics measuring the diversity of income distribution. Okay? So, tie strength, 0 means no overlap. 1 means everyone has the same values. The lower the Gini coefficient, the more diverse it is. And look what we get. So this is an experiment from a computational model of agents. And now we have a nice mathematically describable curve here. So this is a pure computational experiment. Let me set this up for you. There we were looking at a single team. Here we're looking at multiple teams carrying out pseudo design tasks. In computation, it's hard to do designing. You can make up things. And what we're looking at is you let each team do its design task, and at the end of that, and maybe at the end of one design task or end design tasks, a member of one team migrates to another team. And then they do the next design task, and then so on. And what we're interested in here is the diversity or the range of the design space they explore. And I'm going to redo these, but without migration, the number of this is a measure of the diversity of the design space, the number of distinct decision sets that they end up exploring. And if you look here, the mean is somewhere here, 4.5, and this is my teams with migration, and the mean somewhere is around 7. I've forgotten the numbers, but they're fairly clear. A pure computational experiment that has agents that adapt themselves to the value systems of the group they're in. They move, and as a consequence, they force the other team they move to to go somewhere they wouldn't have otherwise gone. And this is a much richer one, and let me build it up for you a little bit, or describe it. What we ended up with is, how do you end up with design styles or schools of design? Where does that come? There's 2 ways. One is, you have a really important individual, and that individual brings people with them. Or what we see much more is it's an emergent property. Emergent means something you didn't put there. And so what this is these are design agents that generate artworks. It really doesn't matter what they're generating. And we've added a word here, which we'll talk about. And what they do is they generate artworks, and based on their own experience, they evaluate them and pick the one that's most interesting and send it out to everybody. And they get the artworks back from everybody else, and based on their experience, evaluate them. And it's a credit assignment problem. They send back and say, I like this one. And that is a process that continues. And if you want to look at this from economic terms, this is an economy full of novelty. That the value that's passed back and forth is novelty. And they're situated and they respond to the works of others. You've got to measure novelty, although today I think I'd call this surprise, but in the original work it was novelty. Novelty is really hard to measure. You'd think it's got to be truly easy. Novelty, right? Just means it's different to anything that happened before. I can generate novel stuff ad nauseum, stuff no human being has ever seen before. Trivial. You know, I take a marker and I can draw a line of some length that no one has ever seen before. And I can continue to do that. You know, it's 1 angstrom different to the last one. You know, 1 whatever different. So novelty can't be that. Plus, if you accept this notion of constructive memory, the past isn't fixed anyway, right? Which is why, you know, the notion of being creative disappears once you've done it, right? Someone copies the iPhone, which they did a lot of, we don't give them credit, right? We give the originator credit. So how can you calculate out things like novelty or surprise? Here's a nice idea that translates into a statistical mathematical description. What you need is a categorization of where you are, which you can do quite easily, and you can determine the probability of the next step in that categorization. So if I was to predict the next step, and then you can measure actually what happens against the inverse of that. So the way to describe that is the failure of confident expectations is surprising. And I'm going to leave you to think about that. And then, you know, these agents have to do things. Most of our programs stop because they've finished doing what we told them to do. We're not like that. I mean, students are like that, but no. Humans just go on all the time. And actually, when you study designers, they don't even stop thinking about the design after the project is finished. They still think about ideas about it. So what's the motivation? In the one we came up with is the idea of curiosity. It's not ours. It's a well-known idea. Curiosity. What is curiosity? It's finding something you weren't looking for interesting. And, you know, as all researchers discover, other people have thought of this. Wilhelm Wundt, who's a German mid-19th century psychologist, studied this and came up with with all due respect, it's a very Germanic model, pain and pleasure. It turns out in the brain we have pain and pleasure centers, so pain and reward centers. But the interesting thing, and by the way, he was studying, I often felt I should put an application in studying hedonism. If you don't know what hedonism is, I feel sorry for you. Hedonism is the pursuit of pleasure for pleasure's sake. In fact, you really have to ask yourself, what are we doing if that's possible? Why are we hanging around doing other things? But anyway, that's a different talk. So, but the interesting thing about this is what the combination curve looks like. If we replace hedonic value by interest, what arouses our interest, intellectually I'm talking about here because I've been reading the news this morning, it's not a normal distribution. It's a really odd, sort of funny distribution that says when the novelty is low, there's not much interest. And then you get this power curve up to here, and at some point it drops down to below 0, meaning pain. And you think, wait a minute. And then you think, wait, let's look at things that were really novel. You know, for 1,200 years or more, Western music was tonal, 12-tone scale. Along comes Schoenberg. If you haven't heard of it, that's because you're an engineer. Schoenberg was a composer in the early part of the 20th century, and he produced atonal music. Like all brand new stuff, the first concert he was pelted with tomatoes and all the good stuff that happens to people like that, because it was just here. And I remember my parents, because I grew up in the 50s when rock and roll was just starting, and my parents always said, that stuff is painful. And they were right. Anyway, we need to move on. Here's the bit of artwork. It actually comes out of CMU. It's a web-based system that people vote on. So we didn't have to do anything, which is always perfect for studies. And this is, you can try different values of novelty, and you get these really amazing things. If you put the peak at 0, it just dies. There's nothing. And if you put the peak way out, I don't know what these numbers mean here. I don't know what the scale is here. But if you put it way, already around about 15, you just get randomness. But in between, you get this structured world. And humans love structure. And in fact, you might even say the role of research is to structure the world. So, what do you get? We started with 10 agents. They all start the same, but with slight perturbations, they start to do different things. The perturbations are the order in which they see the stuff. And lo and behold, after n generations, 5 of them, and that's an arbitrary number, really like each other's work and support each other's work, and don't really like the other people very much. And their work is very similar. Even that one, that's just the intensity is different. And these guys love each other as well. And this guy also has a different intensity, but he's got the same structure. So now we've got an emergent school of design. We didn't have a leader. I have to move on because I want to... Actually, I'm going to skip this slide, but I can't. So just watch it as it goes by, all right? Until we get to the end. But it's a really interesting and important piece of work. Because I want to get to here. I noticed the time, and this slide tells you that designing sits in an ecology that starts at government. Big government or small makes no difference. Starts at government and ends up with consumers who are affected by all sorts of people, and we just sit there. We're not innovators. Innovation is the production of value from intellectual property. Designers may or may not do that, right? And that's a different discussion. But I want to just talk about this. We generate products, and we have consumers, and now there's this world of knowledge about consumer behavior. And I've pulled out that little bit, and let's see what we have. So, these dots are designs, and behind them are companies that have policies about how you replace them. But, that's just sitting there. These white-looking things are consumers, and they have goals about what they want to buy, and then what they find interesting. Now, we've all done this when we're searching, say, not trying to buy, but search is a good example. You go in saying, I'm looking for a paper on, optimization applied to social networks. Do you ever find other papers that are interesting? I hope the answer is yes. The point is that we change our values by what we're exposed to. And so, what's behind these agents are, social, cognitive, situated, adaptive agents. Their social interactions are at multiple levels, but here we're just showing the ones that they interact with other agents, because you can interact with non-agent entities. Like, the New York Times publishes a review of a bit of software. It's really interesting what the effect of that is. If the review is positive, you get a big bump. If the review is negative, you just get a small bump. You get a bump that publishes. It doesn't matter good or bad. So there's lots of stuff going on, which we try and capture a little bit of. So what you're going to see is that these guys interact with each other. It's a little hard to see, but if you've got really good eyesight and a fantastic projector, these change color as their values change. So, oh, no, back. So this is a movie of a window into a spatial view of this. I don't know if you can see, the social lines look to be very dim, but these, and you can see when they consume, and they have this, we've all had this, that when you're trying to buy something, there's so many possibilities. But once you buy it, you tell everyone, wait, you should buy what I bought. That's an example of your value systems changing. Okay, and then finally, you can take all of these ideas and start to build a system where now these are components. Yeah, that'd be really good. I know. Yeah. These are components, and these are constraints. And they're trying to organize in such a way that they, well, no, they're not. Okay, let's do this. So let's run it this way. Nope. You're not going to see that, is all I can say. None of this. So I'm sorry, but you have good imagination. This uses the same agents, just they mean different things, right? And what they're doing, they're trying to satisfy constraints. They also generate constraints. When two things get together, sometimes they produce a new constraint. And so what they're trying to do is, socially, they join together, trying to satisfy constraints, and the end goal is a self-organized beginning of something. It's the best I can describe it to you. It's not published yet, so I can't even point you anywhere. So what can we say about, we're near the end, social design computing? If we look at design computing, that is, we're just using computation in design in the way we normally do it, you can capture it really by y equals fx, where f is an algorithm. You put in x and you get out y. And you shouldn't be surprised you got y, because you put a lot of effort into making sure x goes to y. The only thing that's surprising might be the value of y. If you don't get a y, the algorithm's not working. And that's what computation is. But socially, we get something else. Of course, we run algorithms, because that's the way we drive computers. But we're looking for more than that. What we look for is y is some unknown function of f of x, where y is some emergent property of f of x. And that new function is unknown, and we look for that. So if you saw the teams example, there's no model of how social ties affects the diversity of ideas. There isn't a model. But by doing experiments, we found this emergent response behavior, and which is more direct. It's not very emergent. And then when we do some of these other things, like the migration, there's no model of any kind, and we don't have a good model yet. We just have descriptions of behavior. And so all of these shift from here to here. And this opens up possibilities for us in building computational worlds that didn't exist before. And these people are truly nice people, is all I can say. And let me stop there.